Good morning, everybody. I hope you had a great day yesterday and a good morning so far. It's actually still nighttime here. I just got back from a Cubs game and we won. It was awesome. It was so fun. If you're a baseball fan, I definitely recommend going to Wrigley Field at some point. It's great. Okay, so just to give you a little bit of what we're going to do today, we're going to look at how to do linear expansion. I'm going to show you with an example problem, and then I'll get you to do two of those on your own. And we're going to finish up actually chapter 13 today, and we'll get you to do the 13.2 review so you can get some critical thinking in, because you know how I like those questions a lot to help you think a little bit more. And then, yeah, I'll go over those for you. I'll have a video for you for Friday. And then I will also give you your study guide, and then we'll go over that Monday, and then we'll take your test Tuesday, and then we'll review for your exams. And you will be, pretty much done. Miss Smith is going to be putting some of your grades in right now. I'm going to email her the grades that I want put in there, and so all the work that you do, so like the end of your, when you get done today, turn in all your work to your sub, and then I'll get Miss Smith to go and check and see that you all have done it, and you'll get your grades, since Coach Reese is not here right now because he just had his baby. And then I'm also about to get a list of the people who won't have to take their exam. It might change due to our test on Tuesday, but I doubt it. I don't think that most of y'all are going to have to take it, so that's great. All right, so let's look at the example problem on page 318 about linear expansion. We went over the equation for it yesterday, but I didn't want to give you any homework or anything, so in case you guys wanted to go to church or if you had practice and things like that, and you had to do a lot of problems during class on Tuesday. So let's look at the problem now, and just, if you forgot, look at the top of 318, and it gives you the equation that we're going to need to solve this problem, okay? So it says a metal bar is 2.6 meters long at room temperature, 21 degrees Celsius. The bar is put into an oven and heated to a temperature of 93 degrees Celsius. It is then measured to be found 3.4 millimeters long. What is the coefficient of the linear expansion of this material? Pay attention to millimeters, okay? We're going to have to change that. Always pay attention to your signs and to see what everything is in, okay? And to your metric units. Don't worry about sketching the problem. That's something that I find silly. If it helps you out, then that's great. But I won't count you off if you don't sketch the problem. So let's look at what we know. We know the initial length is 2.6 meters, right? Tells us that right in our problem. 2.6 meters. All right. The change in length. All right, it says the bar is put into an oven and it's found to be 3.4 millimeters longer. All right, we want to get that in meters though, right? So if it's 3.4 millimeters, if it's 3.4 millimeters, if you need to know how to do this, which y'all should have learned from Coach Parrish, that it's 3.4 times 10 to the negative third, because millimeters is 3 points over from meters, okay? So it becomes, the change in length is 3.4 times 10 to the negative 3 meters, okay? It doesn't tell us what it changed to, it tells us what the overall change was, so that's really important there. We also know our initial temperature was 21 degrees Celsius. And we also know to heat it up, the temperature, it was heated to 93 degrees Celsius, okay? So it says, what is the coefficient of linear expansion of this material? All right, we have our equation for that, right? So our equation is change in L is equal to alpha, or the coefficient, right, of L1 times the change in temperature. All right, so let's get that alpha by itself. To do that, all we have to do is divide L1 and change in temperature, and we'll get alpha by itself. So it'll end up being this. I'll show it to you in just a second. Change in T. All right, so this is what we're going to use right here. And I'll just do it in that upper left-hand corner right here. All right, so now all we really have to do is plug in. All right, so we know our change in L, our change in length is 3.4. Times 10 to the negative third meters. All right, and then at the end we have our initial length is 2.6 meters. That's why they have to match up with each other. And then we have our change in temperature. So just subtract that and you'll get, let's see, 71, 72, 72, 72 degrees, or you can keep it 93 minus 21, it doesn't really matter, minus 72, or times 72, and that's going to end up giving you 1.8 times 10 to the negative fifth meters. Sorry, not meters. Celsius to the negative 1. Remember, we went over that's what it looks like there. All right, so just in the top left right here. It's pretty simple. Just have to plug in. All right, remember the unit, like I said, for the coefficient of linear expansion is degrees Celsius to the negative first. Okay. All right, good. Okay, so after we go over the rest of 13.2, which I'll do right now, I want you to do practice problems 8 and 9 on page 319. Okay. All right, we're going to look at thermal expansions in liquids now. All right, so this is going to be a lot of me talking. I'm sorry. But just think, this is the last time you'll have to hear it, so that's good. So thermal expansions in liquids. So most liquids also expand when they are heated, just the way that solids do. A good model for all liquids doesn't really exist, but it's useful to think of a liquid as like a grounded up solid, because it basically is. Groups of 2, 3, or more particles move together as if they were like tiny pieces of a solid, right? So when a liquid is heated, particle motions cause these groups to expand in the same way that particles in a solid are pushed apart. The spaces between the groups will increase. So as a result, the whole liquid will therefore expand. So with an equal change in temperature, liquids expand considerably more than solids, and gases expand even more than that. Okay, so that's important to know. So solids expand less than liquids, and then gases are even more than liquids, okay? So we've learned that water is most dense at 4 degrees Celsius. That's very important to know. And when water is heated from 0 to 4 degrees Celsius, instead of expecting expansion, water contracts as the cohesive forces increase, and then the ice crystals will collapse, right? So at 0 degrees Celsius, it was frozen, and then when you heat it to 4, of course, the ice crystals are going to collapse. So the result is that the liquid form of water has a smaller volume and an equal mass of its solid form. The forces between the water molecules are strong, and the crystals that make up the ice have a very open structure. So, so even when ice melts, tiny crystals are still going to be there. These remaining crystals are melting, and the volume will then decrease. However, once the temperature of the water moves above 4 degrees Celsius, when water is most dense, right, the volume increases because of a greater molecular motion, okay, because it's not, those particles are going to be going away, or those crystals are going to be going away. The practical result is that ice floats, and lakes and rivers and other bodies of waters freeze from the top down. All right, so I bet y'all are like, yeah, that's kind of cool to know, but why is it important? So different materials are going to expand at different rates, as indicated by the different coefficients of expansions in the table 13.2 that I showed you earlier that I'll have printed out for your test. Engineers must consider these different expansion rates when they design different things. So steel bars are often used to reinforce concrete, and therefore the steel and concrete must have the same expansion coefficient. Otherwise, the structure may crack on a hot day. Also, like a dentist must use filling structure materials that expand and contract at the same rate as the tooth enamel, or it could crack again, right? Different rates of expansion are, they're sometimes useful. Engineers have taken advantage of these differences to construct a useful device called a bimetallic strip, which is used in thermostats. So a lot of these are just some real world examples just to show you that, hey, this actually is an important thing and cool thing to know. Bimetallic strip consists of two strips of different metals welded or riveted together. Usually one strip is brass and the other is iron. When heated, brass expands more than iron does. Thus, when the bimetallic strips of brass and iron is heated, the brass part of the strips will become longer than the iron part. So the bimetallic strip bends with the brass on the outside of the curve. If the bimetallic strip is cooled, it bends in the opposite direction. The brass then on the inside of the curve. If you look at figure 13-19 at the top right here, a bimetallic strip is installed so that it bends towards an electric contact as the room cools. Figure A right there is kind of neat to look at. When the room cools below the setting on the thermostat, the bimetallic strap bends enough to make electric contact with the switch, which turns on the heater then, right? So this is all going on in your houses if you have central air heating, okay? As the room warms, the bimetallic strip bends in the other direction. The electric current is broken and the heater will therefore then be switched off, right? All right. Those are just some real world examples to show you that this is actually a pretty relevant thing. A lot of times I get those questions in math and things like that. They're like, why does this matter? Well, here, this is a reason why this really does matter. Actually, multiple reasons. All right, and let's look at plasma. So if you heat a solid, it melts to form a liquid, right? Further heating results in a gas. So what happens if you increase the temperature even further then? Collisions between particles become really violent, enough to tear the particles apart. So electrons are pulled off the atoms, producing positively charged ions. So like a gas-like state of negatively charged particles, which are electrons, and positively charged ions, these are going to make it be called plasma. These are going to be called plasma. So it's another fluid state of matter, though, plasma is. The plasma state may seem uncommon. However, most of the matter in the universe is actually plasma. So stars consist of mostly plasma. Much of the matter between the stars and galaxies consists of energetic hydrogen that has no electrons. This hydrogen is, therefore, it'll be in a plasma state, right? The primary difference between a gas and plasma is that plasma can conduct electricity and gas cannot. So make sure you know that, okay? That's very important for us to know. A lightning bolt is in the plasma state as well. So neon signs, if you look at figure 13-20 of some sort of weird Hollywood sign, they have fluorescent bulbs, and the sodium vapor lamps contain glowing plasma. So that's how you get the fluorescent look there too. It's plasma actually. So that's just another just interesting part about this chapter when it comes to liquids and solids and temperature, with like you can heat something even further from a gas, and then that this can occur. All right, so let's see. Yeah, this is kind of a short lecture because I want to give you a chance to do your work, because it will be turned in at the end of class, and what you don't get done, you won't get credit for, okay? So I've given you 2 problems to do. Let me see here. Okay, actually, I want you to do all of these practice problems because it is such a short lecture. It's only a 15-minute lecture. So I actually want you to do all these practice problems on 1319, and then I want you to do the 13.2 section review, 2.1 through 2.4. You aren't going to be graded for right or wrong, but I want to see that you at least attempted them before the end of class today, and turn them in to your substitute teacher. I'm not exactly sure who it's going to be, but turn them in, and then I will let Miss Smith know to come check them, and you guys will get your points for the day. It'll be 15 points, so that can help boost your grade just a little bit before this last test, and yeah, the study guide should help that as well. And I will go over those problems tomorrow just to help clarify some understanding and all of that, and then you'll have your study guide to work on over the weekend. For some reason, I think that you might have games today for Thursday. I think you'll have games today, so good luck to you all, and I hope you do really, really well. I'm going to find out from my sister how all the teams do. So I'm thinking about you all and praying for you all, and y'all are so close to being done, and I'm so proud of everything that y'all have done this semester. All right, I will talk to you on Friday. Have a good day.